Greetings, aspiring scientists. Today we'll continue my lecture on ionic bonding. If you watched my last video, we'll take up right where I left off. So let's go to my slides. So we're in 2.1.2. Really, we've already talked actually a lot about 2.1.2 and 1.3 in my previous video, but I'm going to go a little bit deeper here and review some things. Okay, so here we are, ionic bonds. So I need to introduce something called electronegativity. This will be a core fundamental idea that you will use to answer and give reasons for many questions. So it's important to define it properly. So this is written as xp. I think it's actually the Greek letter chi. Looks like an X. Subscript p. On the Pauling scale. I think that's the name of the scientist who worked on electronegativity. This is defined as the relative attraction that an atom has for electrons in a shared bond. And a shared bond means shared pair or pairs of electrons. That's actually the definition of a covalent bond, not ionic, which is strange that we need to introduce it here, but you'll see that it is useful for discussing ions in ionic compounds as well, and the properties of ionic compounds. And here's an example of actually a covalent molecule, HF, hydrogen fluoride. And the thing is, you can see that the pair of electrons is not actually shared evenly. Okay, if we look at this color density kind of profile where red is more electron density and blue is less, you can see F actually holds more of the electron density, holds it more of the time than H does. If you end up drawing Lewis structures later on, quite soon actually, I usually like to draw the electron pair closer to the more electronegative atom. So there's a pair of electrons being shared, but it's way past the halfway line in between these two atoms. It's closer to fluorine instead. So we can say in this case, sort of qualitatively, that fluorine has greater tendency to hold that electron, greater electronegativity. And we can compare these to other types of covalent bonds with other atoms and build a kind of scale, and then assign actual numbers and quantitative scaling to this property. So here, fluorine has higher electronegativity, more electron density in the orange and red. H has less. In other words, when an atom is sharing electrons, how much electron density is taken by one atom or conceded by the other, given up by the other one? Very important idea. So this scale essentially goes from 0 to 4. The Pauling scale, 0 being the least electronegative and 4 being the most. So up in the top range, we have what are known as sort of the most electronegative nonmetals. They're near the top right side of the periodic table, excluding the noble gases, of course. So things like nitrogen, oxygen, fluorine, and chlorine are very electronegative. Then we have kind of the mid-range 2.0 to 2.9. These are other nonmetals, maybe things like sulfur, phosphorus. And then 1.5 to 1.9 is the metalloids, or things that are near the bottom of the periodic table, or along the metalloid staircase, if you've learned about that. So these are lower than the nonmetals, but they still have some electronegativity. And then we get to the metals, especially down low will be the left side of the periodic table, the alkali metals and the alkaline earth metals, less than 1.5. Okay. So these actually do appear in the data book. In section 9, you have a periodic table that I think has a bunch of things, electron affinity and electronegativity and maybe radius or some other things, but I think the electronegativity is the big number that's right in the middle. You should get used to searching the electronegativity up for various elements. So there are some trends in electronegativity, some patterns that we can observe around the periodic table. I've created this kind of 3D visualization of a periodic table with electronegativities as sort of the third dimension or third axis going up and down. So things that are higher have higher electronegativity, and they'll have a more blue color, whereas things that are lower, I think, have a more yellow color. Let me just play this little animation so you can have a look. So you can see in the bottom left is where the absolute lowest electronegativities are, and in the top right, excluding the noble gases, is where the highest are. One more time. So the highest are those things like fluorine, oxygen, nitrogen, chlorine, as I said. And the lowest will be the alkali metals in the bottom left corner, like cesium and francium and rubidium. And there's sort of a pattern on its own in the transition metals in the green section in the middle. We're not really going to look into that too much. But the general trend is as you go from the bottom left corner to the top right. Okay, the general trend is as you go from the bottom left corner to the top right, electronegativity increases. That wasn't quite the angle I wanted, but the top is that large blue box, and the bottom is that very short yellow on the left. And so decreasing would go in the opposite direction, right? Going from top right to bottom left. Very good trend to at least keep in your mind. Okay, so what can we say about this? Well, bonding type is related to electronegativity. The electronegativity scale, and specifically what you're usually going to be interested in, is the difference in electronegativity, delta chi or delta x. This can be used to predict what bond type is going to be made between these atoms. So if you have a difference of greater than 1.8, delta chi greater than 1.8, generally we label that as an ionic bond. Okay, one atom is going to take the electron so much that it will become an ion, and we'll get an ionic lattice solid at standard temperature and pressure. But I would say if we have between 0.4 and 1.8, kind of in the middle region for the electronegativity difference, we're not going to have ionic. One atom will not take the electron pair enough, or the single electron enough, to become an ion, so they will have to share, these two atoms will have to share a pair between them. That's called a covalent bond. But one atom will still hold that pair slightly closer than the 50% line. We'll call it polar covalent. And then if we have a difference of less than 0.4 or around 0.4, we'll call that non-polar or pure covalent. So in this case, one atom really doesn't take the electron or the pair of electrons closer to itself. It really is shared quite evenly between the atoms. And I know my textbook and several textbooks say polar covalent is basically anything above 0, and pure covalent or nonpolar is 0 difference only. You really only get 0 difference when you have pure elements, something like H2 gas or O2 gas or N2 gas. Of course, you'll have an electronegativity difference of 0 there because you have one number minus itself when you check the difference. But there are other combinations of atoms that essentially behave nonpolar. They don't have much shift in that shared pair of electrons between them. It's held at the halfway point, you can imagine. So especially for organic chemists like myself, I mainly focus on that. When we see a carbon-hydrogen bond that has an electronegativity difference of around 0.4, we essentially call it nonpolar. Compared to other things, the electron pair does not belong on one atom more than the other. So that's why on this slide I'm saying let's say 0.4 roughly is the cutoff point for polar and nonpolar. Okay, a little practice here. Predict which of the following will have an ionic structure: sodium fluoride, NaF, lithium iodide, LiI, or aluminum chloride, AlCl3. So if you check the electronegativity difference of these, if you check sodium, I think the electronegativity is about 0.9. Fluorine, 4.0. So this difference, delta chi, is going to be quite high, 3.1. I would definitely predict that is ionic and has most of the properties of ionic compounds that we have been and that we will talk about. Lithium iodide, what can we say about that? Its electronegativity is 1.0, very similar to sodium. Then we've got iodine, electronegativity 2.7. So if we look at this, this will have a delta chi of 1.7. 2.7 minus 1.0. So we can classify this as not ionic, generally based on the IB guidelines. However, this will be a polar covalent bond that's so polar it's nearly ionic. So it's going to start to have properties of ionic compounds that we have talked about actually. And this is where we have to sort of see that this is not a black and white distinction between covalent and ionic. It's a spectrum that slowly shifts from one to the other, and this electronegativity scale can tell you at what point on that spectrum it is. So we can call this polar covalent, but it's going to have some properties of ionic compounds for sure. Then aluminum chloride. So how about aluminum? I think that's 1.6 electronegativity. And chlorine, 3.2. So this delta chi, or electronegativity difference, will be 1.6, even slightly less than lithium iodide. So this also not ionic, although still fairly polar. And IB loves to use AlCl3 as an example of a type of compound that has bonding right in the middle of various types. So this will have properties of ionic and covalent, perhaps even metallic slightly. Okay, so our answers would be these on the right. Sodium fluoride has a huge difference of 3.1. It's clearly ionic. The other two are not as clear, but we'll label them as not ionic. Okay. Some notes about this. You can often make reasonable assumptions just by looking at the periodic table if you need a quick check. So elements that are farther away on the periodic table will have higher electronegativity difference. Because of that general trend I showed you, where it's lower in the bottom left and higher in the top right. So generally things that are farther away have a larger difference and more ionic character. Elements that are closer together will have less of a difference. You'll have non-metals together and metals together, right? So that's less ionic character. So from the previous slide, lithium fluoride, those are quite far away, but aluminum and chlorine, from aluminum chloride, those are quite a bit closer together. So it's less ionic. All right, I want to talk again a little bit about polyatomic ions. I've introduced these, I think, previously when I talked about ions in a previous video, but again, let's review and build on this. There's many examples of compound molecules, so not ionic bonding per se, but these are molecules with covalent bonding that contain a charge in their normal stable form. In this case, we don't call them molecules, we call them ions, but they have more than one atom, so we have the special word polyatomic in front. Poly means many, atom means atom. So polyatomic ions, I'm sure you know some. There's many examples. There's unlimited examples, but I have about 6 here to show you. Nitrate, NO3-, ammonium, NH4+, thiosulfate, S2O32-, phosphate, PO43-, hypochlorite, ClO-, hydroxide, OH-. So, why do I bother talking about this right now? Well, we're going to start seeing a lot of formula and examples with these polyatomic ions and various other things, and you're going to be expected to know what I'm talking about and what your textbook is talking about and what the IB exam is talking about. So this is one of the first things where I have students just memorize sort of a list. I don't necessarily think that you need to sit down and, use flashcards or just memorize these one by one. You can start by just doing practice questions and checking the ones that appear as you need, and you'll sort of get used to it. But in the end, if there's any of these you don't remember, you should come back to this slide and specifically try to remember the ones that you don't see often or that you tend to forget. So learn all of these. The polyatomic ions in the top right. Ammonium, NH4+. Carbonate, CO3 2-. Hydrogen carbonate, HCO3-. Hydroxide, OH-. Phosphate, PO4 3-. Nitrate, NO3-. Sulfate, SO4 2-. Okay, the sooner that you can memorize this name, this spelling, this chemical formula, and this charge, the easier you'll have studying the rest of the content for this class and this topic, and chemistry in general. So practice going from the name to drawing the formula and charge, and then also looking at the formula and charge and writing the name. I also have a list of acids on this slide that you're going to start to want to remember as well. So underneath here, hydrochloric acid, HCl, hydrobromic acid, HBr, hydrofluoric acid, HF, hydroiodic acid, HI, and then nitric acid, HNO3, sulfuric acid, H2SO4, phosphoric acid, H3PO4. So none of these acids have charges in their natural neutral form. I think most of these are strong acids, except for maybe HF. You'll learn about strong versus weak acids and bases later, but just so you know, this list mostly contains strong acids. And a definition I've given you in a previous video of acids is that they tend to release H+. They release protons into solution, aqueous solution. So there's actually some connections between these acids and the polyatomic ions that I mentioned in the table above. For example, if HNO3 loses an H+, it will go to NO3-. It's lost a positive charge from that proton, so it goes to minus charge. So nitric acid, when releasing its acid proton, H+, will become nitrate. Sulfuric acid, when releasing 2 protons, will become sulfate. Phosphoric acid, when releasing 3 protons, will become phosphate. Water, when releasing 1 H+, will become hydroxide. That's an important idea as well. And there's a relationship between carbonate, hydrogen carbonate, and another acid that's not on this list called, or not an acid, actually, yes, an acid, sorry, carbonic acid, H2CO3. So if that loses a proton, it can become hydrogen carbonate, HCO3-. If that loses one more proton, it can become the one above it, carbonate, CO3 2-. So a lot of these things are connected together, and once you see the patterns and relationships, it's going to be easy to remember those steps and the names and the formula and the charges of all these things. So some rules: anions usually finish with ate or ite when they are bonded with oxygen, which most of these are. If they're not bonded with oxygen, anions finish with IDE. We've discussed that in my previous video as well. So oxygen oxide, nitrogen nitride, sulfur sulfide, the suffix changes to IDE. But when oxygen is involved, it will be changing to ate most of the time, sometimes ite. Cations often finish with their base metal name. So from my previous video as well, we know metals, when they're in ionic compounds, don't change their name. Sodium is sodium, lithium is lithium, potassium is potassium. That part of their name doesn't change. For non-metals, you might see some change though. We might have the IUM suffix added. For example, ammonia, NH3, when it becomes an ion, a cation, NH4+, at the top here, it's going to be ammonium. I think that's true for most nonmetals that become positively charged. Okay, moving on. Naming practice. State the names of the following ionic compounds. BaCO3. Alright, so you're going to need to either remember some of those polyatomic names from the previous slide, or go check it. If you need to check it, that's fine. So A here, we're going to have barium, that name doesn't change. Carbonate, CO3, 2-. RBF. Some of you might not know what RB is, but that's rubidium, an alkali metal. Its name will not change here, rubidium. Fluorine will change to fluoride. Get used to the spelling of fluorine and fluoride and fluoro. Sorry, this is IDE, fluoride. C, NH4HCO3. That's a pretty big challenge here. You have to know where two polyatomic ions are in this formula, where that halfway point distinguishes a cation versus an anion. So this is something you probably just need to get used to, but you can identify an NH4 group here from my previous slide. So that is ammonium. And then we've got an HCO3 group. You can also see that on my previous slide as the anion. That's hydrogen carbonate. So the word hydrogen represents the H. C is represented by carbon, and then 8 identifies that we have oxygen bonded to that anion. Ammonium hydrogen carbonate. Next, Al2S3. This will be an aluminum compound. Its name doesn't change. If you're in Europe, you might call this aluminium. That's fine. Aluminum sulfide. IDE suffix for that anion. E, ALP, that's also aluminum, but in this case, phosphide. Usually phosphorus. Turns out we changed that suffix after the pH, the second pH, POSPHIDE. Aluminum phosphide. And then F finally, SrOH2, that's strontium hydroxide. Strontium's name stays the same from the periodic table, and then polyatomic ion OH- from my previous slide, strontium hydroxide. Okay, so you can usually find similar things, other examples on Google, or, AIs like ChatGPT, check your answers. Okay, what's next? So, in the previous practice, what we did is looked at a chemical formula and named it. But you also need to be able to look at a name and generate the chemical formula, and that's quite a bit more difficult. You need to know some chemistry knowledge to be able to do this, because the names don't actually give so much direct information. So you will need to predict how each component will reach its octet, its stable outer shell of 8 electrons, and what charge it will have once it does reach its octet. You will then need to balance the charges between the cations and anions so that the total charge of the whole ionic compound, which is the repeating unit inside the crystal structure, that has a charge of 0 generally. So that means the cation plus the anion, the sum of their numbers must equal 0. Consider aluminum oxide to start. What is the formula? Let me go to the top right here just a little bit. Aluminum is in group 13. To reach its octet, it needs to lose 3 electrons generally. It's going to go 3 plus, oxidation state. Lose 3 electrons. Oxygen is quite close to having an octet. It needs to gain 2 electrons though, so it's going to go 2 minus. So we could pair these up, ALO, but that compound plus 3 minus 2, this compound would have still a charge of 1 plus, ALO plus. And that's not how it works, okay? Ions in ionic compounds in the balanced crystal lattice structure have 0 net charge for 1 repeating unit. So this is not going to be what happens. So here's a little trick. We need some common multiple of these ions that will cause these charges to balance out. And if oxygen is 2 minus, you can take that 2 number and put it with the cation. Take 2 of that cation. Check the cation's number. It's 3 plus. Take that number 3 amount of the anion. Al2O3. So I think if you count up all the charges on all the cations and anions in this, you'll find its charge is 0 overall. We have 2 times plus 3 for the aluminum, and we can add that with 3 times minus 2 for the oxygen. And what do you know? We'll get plus 6 minus 6, that's 0. And that is the requirement for repeating ionic unit in a compound like this. So Al2O3. This is kind of a difficult idea, but I have a bunch of practice on the next slide. We can give it a shot. So here's a bunch, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, I think. If you want to try by yourself, try it, and then I'll go through the answers here. So calcium nitride. Calcium is going to lose 2 electrons, and nitrogen is going to gain 3 as its easiest way of forming its octet. So we're going to have Ca2 plus, N3 minus. We're going to swap those numbers just like I did for aluminum. So in the actual chemical formula, the compound formula, we're going to have Ca3N2. That way the charges will balance out. We'll have plus 6 on the left, minus 6 on the right, 0 total. Okay, calcium oxide, much easier. Calcium goes 2 plus, oxygen goes 2 minus. So we can just write one of each here. Calcium oxide is just CaO. Sodium carbonate. So you've got to remember carbonate. What's the charge on that? Hopefully it comes to you. It is 2 minus. That means we're going to need 2 sodiums, Na2, CO3. Sodium carbonate has 2 sodiums to balance the minus 2 charge on CO3, 2 minus. Aluminum nitrate. Aluminum will usually go 3 plus. Nitrate is 1 minus charge, so we're going to actually need 3 nitrates. And when we do this, have 3, like 2 or 3 or 4 or whatever number of polyatomic ions, write it in a bracket. NO3 in brackets, and we're going to need 3 subscript on those brackets. This is just a clear, nice way of showing that you have a polyatomic ion in multiple numbers. Okay, magnesium oxide, easy one again. Mg goes 2 plus, O goes 2 minus, so MgO is fine. Sorry, that's an O, not a 6. Okay, strontium chloride. Strontium goes 2 plus, so we're going to need 2 chlorines. Chlorines go 1 minus, oxidation state. SrCl2. Sodium sulfide. Sulfur goes 2 minus, sodium goes 1 plus, so we're going to need 2 sodiums to balance out that sulfide. Na2S. Lithium nitride. Lithium goes plus 1, nitrogen goes minus 3, so we're going to need 3 lithiums to balance out a nitride, N3 minus. Li3N. Lithium nitrate, though, now nitrate is a very different structure than nitride. We'll just need 1 lithium bonded with an NO3 minus group. This will have a net charge of 0, that's fine. Barium hydrogen carbonate, long name. Barium will go 2 plus, I think. That's in group 2. Alkaline earth metal. Hydrogen carbonate has a charge in between carbonate and carbonic acid, so it's going to be 1. So we're going to need 2 of that, actually. Again, in brackets, we need this time. Okay, so this is going to require 2 hydrogen carbonate groups. They're 1 minus each to balance out barium's 2 plus. Oh, let me get yellow again. HCO3. 2 of those in brackets. And then finally, ammonium phosphate. Okay, so we know ammonium is NH4. It is 1 plus. Phosphate, PO4 3 minus. So to balance out this, we're going to need 3 ammonium groups that are 1 plus each. So again, in brackets here, NH4 3 PO4, ammonium phosphate. Okay, moving on. So that brings us to 2.1.3, ionic lattices and properties of ionic compounds. So I'll remind you what the ionic structure basically looks like. It's repeating units of the ionic compound formula in a lattice type crystal structure that extends trillions and billions and trillions of units in every direction. So ionic compounds form a solid crystal with a particular lattice structure. This structure depends on the size and the charge of the atoms and the way that they stack together. This lattice is non-directional. This is actually an important idea that you can use to explain some things, but it means each ion feels equal forces in all directions. This is a strong bonding property because it means there's no particular weakness in any one direction, so it doesn't matter whether you apply force or impact or energy in one direction versus the other, like lengthwise, up and down, diagonally. Generally, the bonding is non-directional in ionic compounds, so they're equally strong, and they don't have weak points like that. So this chemical formula becomes the smallest repeating unit. So in my example of NaCl here, you can copy and paste an Na and a Cl that are ionically bonded over and over and over again to generate this structure I have in the top right, and to basically infinitely or near infinitely generate the entire crystal lattice structure. Alright, we need to discuss something called enthalpy. This might be the first time I've talked about it in my videos. There's a whole unit about enthalpy later on in this curriculum, but for now you can just think of it as energy required to do something. And it has a special label, delta H, for enthalpy change. Enthalpy is given the letter H, capital. And the standard, the little circle in the top right as a superscript, I think just means under standard conditions. So something like room temperature, you can imagine room pressure. So this enthalpy usually has units of joules per mole or perhaps kilojoules per mole. So we're not really finding the enthalpy required to do something to one atom or ion, but for a mole's worth of atoms or ions. This represents the energy required for a particular process to happen per mole of the target compound. So the first one that we will consider is lattice enthalpy, or lattice energy. Delta H standard, subscript lattice. This represents the energy required to separate a solid crystal into individual gas ions. So I'd like you to imagine the lattice on the previous slide here, NaCl. If I were to just take one ion, maybe the chloride in the top left corner there, and just apply force and energy and pull it away, if I pull it enough, it will escape all the electrostatic forces and the electric fields of the ionic crystal and become a free ion. Once it's free like that, it's a gas. It's not in the liquid or solid phase, but it's still an ion. It's still the chloride ion Cl-. So that's what we're trying to measure with the lattice enthalpy. We want to just separate the ions from the ionic solid crystal structure. So what can we say about this? We can draw a little formula actually. Mx we can say is our metal, our cation in the ionic compound. X is the non-metal or the anion. So it begins as a solid salt, ionic salt, and then we'll separate it into M plus gas and X minus gas. Just rip those ions out of the structure into gases. So it turns out this energy, delta H lattice for this process, is always greater than 0. It requires you to put in your own energy to accomplish this, to separate these ions. If it didn't require your energy, they wouldn't be stuck together in the first place, right? Nothing would be holding them together. They would just fall apart. So delta H lattice is always greater than 0, a positive number. If you remember back in my discussions about temperature and state changes, we said that processes that take energy from the surroundings are endothermic. This is very much related to that. So we have to put in our energy to a pot of water to boil it to a gas, right? Similar thing here. We have to put in our own energy or energy from the surroundings to separate ions into gas phase from the crystal structure. So this is also endothermic, we can say. The enthalpy or energy must be greater than 0 in order to separate a positive and negative ion. This process is sometimes equivalent to sublimation. That's a state change that we discussed in a previous video. Solid to gas is sublimation, and really that's what's happening here to our ionic salt. What else? Okay, so lattice enthalpy varies mainly with ionic charge and atom size, atomic radius. Greater charge will mean stronger attraction between ions and therefore higher lattice enthalpy. And the thing that I have that can help you describe this is Coulomb's law of electrostatics. We can write this as the force of electrostatic attraction is proportional to Q1, Q2 over R squared, where Q1 is maybe the cation charge, Q2 is the anion charge, and R is the distance between them. And we can kind of treat it as the distance between the center of the ions, I think. So if their radius gets larger, the distance between the centers actually gets larger, right? We have to consider it that way. So greater charge, greater Q1 and Q2 will make this force higher. That's going to require more energy to separate. Also here, larger radius will mean weaker attraction between ions and therefore lower lattice enthalpy. R gets bigger on the right here, F gets smaller. Okay, do we have any data to show this? Yes. So here's some things we can compare. MgO, magnesium oxide, with NaCl, sodium chloride, with KBr, potassium bromide. So the lattice enthalpy for MgO, compared that with the other two, is a huge increase, 3795 kilojoule per mole versus 769. And what are the features of these? So if we kind of take NaCl as the standard, what's the difference between NaCl and MgO? The main difference is that we have Mg2+ and O2- in MgO, whereas we had Na+ and Cl-, just one charge on NaCl, but two positive and negative charges on MgO. According to that Coulomb's electrostatics law on the previous slide, this has much greater charge, essentially double for each, the cation and anion, so you would expect maybe 4 times as much force and energy required, and roughly kind of is. We can then compare NaCl to KBr. NaCl has a higher lattice enthalpy, not by a whole lot, but about 100 kilojoule per mole. That's not negligible. There's something going on there. And the way that we explain this is because K and Br have larger ionic radii. So the distance between the centers of those ions is going to be larger than NaCl. In the equation I had on the previous slide, that means R is larger, that means the force is weaker, and the energy required to separate them is less. Now, something that I think should be pretty clear here is that charge has a greater effect on the lattice enthalpy. And it's because when we go from +1 to +2, we are actually doubling the charge. The fundamental Coulomb charge value of that does get doubled. But for radius here, we're just having some small percent increase, maybe 5 or 10%. Some of them might get up to 15 or 20%, but we're very rarely doubling the radius when we're comparing ionic compounds here. So that's why there's not as big of a difference between compounds with different radius. And you can see that again here. If we just compare all of the halogen, the sodium halides, NaF, NaCl, NaBr, Nai underneath here, the general trend is as that anion gets larger, iodine has the largest radius, the lattice enthalpy goes down. But not by a whole lot, it's just a little bit each time. I wrote increasing cation radius here, that's actually anion, I think, sorry. Not cation, anion. Because the cation Na is the same every time. Okay. So a little bit of practice here. Write an equation that represents the lattice enthalpy of MgCl2 solid. So we'll start with that. MgCl2 solid, that's our ionic solid compound. We'll input some energy. We will get Mg2+ gas now. It's no longer in a solid structure. And Cl- gas. But these equations also need to be balanced just like any chemical equation or physical equation. So 2 chlorides need to be released when we break apart one ionic unit here. It has Cl2 in it, so we'll get 2 Cl- out of that. Okay, part 2, state and explain which of the following would have the highest lattice enthalpy value. MgCl2, Na2O, MgO. Okay, so these might have some differences in their atomic radius, but really it's the charge that will greatly affect the lattice enthalpy. So Mg will be 2+, Cl will be 1-, Na will be 1+, O will be 2-, Mg will be 2+, O will be 2-. So these ones having the greatest charge will have the greatest electrostatic force of attraction and require the most energy to separate. So require the most energy of this list anyway to separate. And that's what the lattice enthalpy is. Okay. I think we're almost done here. We should talk about dissolving a little bit. So what happens when ionic salts dissolve in water specifically? Well, it's a little bit complicated, but basically around the edges of our salt crystals, we'll have H2O molecules come and approach. We know H2O is an oxygen with two hydrogens attached. But I'll also tell you now that H2O is a very polar molecule. The electronegativity difference between H and O is fairly high. And O is going to hold the electron density more than H. And that means even when this molecule is completely bonded, there's going to be regions of positive and negative within it. So here we have a sodium cation, and we have waters around it. But we know water is polarized. It has negative regions near the oxygen. These are very attracted. And once enough of these surround a sodium cation on the edge of a salt crystal, there's really nothing holding it to the crystal anymore. It could rather be attracted to the water molecules nearby and just separate away from the crystal. This will be a bit of an equilibrium. It might separate and reattach several times, but overall, at room temperature and pressure, things like NaCl will be pulled away by the water molecules over time and will what we call dissolve. Same thing can happen with chloride. It's just the different part of the water molecule affects it. Chloride, this ion is minus, and we got little positive regions of our water molecule surrounding this. Once enough surround it, it can be pulled off, maybe reattached, but over time, the net effect is the crystal falls apart, and we just get dissolved chloride ions. So most ionic salts dissolve well in water for this reason. What about something like gasoline? Gasoline, these black balls are carbons, and the white ones are the same as what we had in H2O, they're hydrogens. So the electronegativity difference between carbon and hydrogen is much less. As I said, organic chemists tend to label the CH bond as non-polar. It's around 0.4 difference, I think. But you can also look at the direction of all of these bonds. In water, the bonds are sort of pointing in one direction of the molecule. But here, we've got like an equal number going left versus right, up versus down, forward versus backward. All of those little vectors that contain the polar bonds cancel out to zero in the end. That's something we'll talk about later in polarity. But something like gasoline, a non-polar molecule, has no attraction, no electrostatic attraction to an ionic salt. It will not surround these ions. It will not pull them away from the crystal structure. It doesn't dissolve them. All right. What about conduction? I've mentioned that ionic salts in the solid phase don't conduct electricity well. Let's discuss that. Also, pure water does not conduct electricity well at all. A lot of people think water conducts electricity because they've been watching Pokemon or something, but pure H2O is a bad conductor. Also, pure ionic salts are bad conductors. You can look at the middle picture here. If I stick two electrodes and a battery and a load into a salt, it's not going to light up this light bulb. So what is required for electrical conductivity? It is something called mobile charge carriers, I would say. Mobile meaning able to move or free movement. Charge meaning positive or negative charge. Carriers. So these can be protons, electrons, ions, whatever. So they need to have a charge and they need to be free to move. Water or an ionic salt is missing one of these things. Water is free to move, but has no charge. It's just H2O. It's not an ion. Ionic salt is very charged, but it's not free to move. It's locked in a solid crystal lattice structure. The molecules, the atoms, the ions can only vibrate. They can't actually translate left and right very far. But a magical thing happens when we dissolve salt in water. The ions from the salt provide the charge, and the liquid state of water provides the mobility. These ions are no longer locked in place. They can shift left and right or whatever. Generally, they'll both go the same direction, so my picture's a little bit messed up here. We should probably have positive only going right and negative only going left, for example. But the point is they're free to move. So when mixed together, ionic salts provide the charged particles, water provides the mobility and fluidity. The solution now conducts electricity, and even a little bit of salt can make an aqueous solution a good conductor. All right. So, question then, are all ionic salts soluble in water or polar solvents? The answer is actually no, but most of them are. Here's a table I did borrow from the textbook I've been using, Oxford Chemistry Course Companion. So you can see a lot of combinations here are soluble. Lithium nitrate, ammonium, ethanoate, barium chloride. But when we get to the bottom right corner here, there's a section where they become slightly soluble or insoluble. So it looks like this is generally higher molecular weight cations and maybe anions. They become less soluble, less able to dissolve in water. Unfortunately, we don't really get into that. Well, fortunately or unfortunately, it's not something you really need to study and know. But just know that not all ionic salts are perfectly soluble in water. And they will form generally an equilibrium, which we will study later on as well. Properties of ionic compounds. So this is a review slide, but I want you to now think about why these things happen. Why do ionic compounds form solid crystals? Well, it's generally because the ions are very attracted to each other, not only to one single partner, but the ionic unit, for example NaCl, is attracted to other ions and other ionic units around it very strongly. So each ion is bound to like 6 other ions around it. Top, bottom, front, back, left, right. So that makes a solid where the particles are not free to translate or shift left and right. They can vibrate a little bit, but not really move out of their crystal structure. Okay, this time consider why. Why would these be hard and brittle? So hardness we can think of as a physical property. If you want to break something apart, you have to break the bonds. Ionic bonds are fairly strong, and we have a lot of ionic electrostatic attraction going on. So you would need to put in enough energy to separate that ion from all the opposite charges around it. You know, if you've got a negative charge with 6 positives around it, that's going to require quite a bit of energy. That makes it hard. Brittle, though, so these compounds are not flexible, they're not malleable, they're not ductile. You can't reshape them. If you apply a force and try to do that, what you instead do is just break the bonds and form a crack, essentially. And you break your solid piece into chunks or powdery pieces. This is a property of ionic compounds, and I think it's just because the ionic lattice isn't flexible. It can either break or be together, nothing really in between. We'll see that metallic bonding later on has layers which can slide around and reform, but ionic compounds are not able to do that. High melting and boiling points, very similar to their hardness. So we've got ions that are bonded to many other oppositely charged ions around them. That's going to require a lot of energy to remove them, and requiring energy to change state is one of those similar requirements. Crystal is an electrical and thermal insulator. So when we have a solid ionic salt, charge does not flow through it well, heat does not flow through it well, and it's because all the particles, again, are locked in place in the solid crystal lattice structure. No mobile charge carriers, no electrons moving around to help transfer kinetic energy, such as might happen in other metallic compounds, for example. They often dissolve well in polar solvents, not always, but usually water will dissolve ionic salts. The polar water molecules can surround the ions on the edge and pull them away. Molten or aqueous salts conduct electricity well. Just like I had on the previous slide, water provides the mobility, breaking apart the crystal lattice structure, but the ions provide the charge that water didn't have on its own. So you should really try to remember these things and the reasonings that I'm given. They often appear on IB exams, I would say. It does not dissolve well in nonpolar solvent. As I said, things like gasoline or vegetable oil or whatever, they have no polar regions or not enough to be attracted electrostatically to these ions. That brings us to the end. This video is getting long, so our guiding question was, what determines the ionic nature and properties of a compound? So its properties in nature are things like its melting point, boiling point, solubility, conductivity. What determines those? Well, it's really the electronegativity, right? The electronegativity difference between the cations and anions, their radius, the geometry of the crystal structure. Those things determine the nature of the actual compound material itself. All right, it's a good place to stop. Next time we'll move on to covalent. We've actually finished everything with ionic, so if you followed along, that's great. That's all you need to know. Next time we'll do covalent and Lewis structures. Covalent compounds are quite a bit more complicated, and there's a larger variety of them, we could say. Thank you for listening. Good luck studying. See you next time.